All right, so in this problem, we are asked to modify a part, and modifying parts, specifically parts with fairly complicated configuration trees and things like that, is a common question on CSWP. Really, the edits here are pretty simple. The easiest way to get caught up is just not managing the configurations properly. So none of the edits here are complicated. It's just knowing how to do the configurations. Maybe on the instances to skip for the pattern could get cut up on a couple people. So we'll go through that real quick, and if you have any questions, stop me and we'll talk about it for a little bit. First thing I want to do is I want to make a new configuration. So I'm going to go to the configurations tab, add a configuration, give it a name. I'm just going to call it big because that's what I'm told in the instructions. Once I've got that, now I need to be careful about when I make a change, how do I apply that change to the part in terms of all the different configurations? The first thing I'm asked to do here is to set the wall thickness and flange width to 4 and 20 millimeters respectively. So since I'm told those are global variables, right? I'm just not told, it just says set wall thickness. I'm going to assume they're global variables because they're given as names. So I'm going to check here, going to tools, equations. There they are. Now you'll notice here when I click on the box, I get a little drop-down menu that says, what am I going to apply this to? All configurations, this configurations, or specified configurations. A lot of times if you're making configurations, you're doing it because you want to have different kind of settings for those different pieces. In this case, I want to just have the big configuration, have a wall thickness of 4 and a flange width of 20. Again, I'm just going to apply that to just this configuration. And when I do that, you'll notice that the little box kind of shows there. And I can click on OK. And now I have these new configuration, this new configuration with this thicker walls and the bigger flange. And if I go to my default, it's going to automatically kind of keep what I wanted inside those settings. So that's the first thing. And you can do that for pretty much any feature. You have a question, Martha? The configurations? Yeah, so in the equations, whenever I click on one of these values, if I have more than one configuration, I have to make the configuration first. It doesn't give you the option unless you have multiple configurations. Then I can choose how I want to apply a change in a value inside the equations. So I can have totally different equations for different features based on the configuration. That's allowed, right? In this case, I'm only applying these values to the current configuration, which is the big. And then it'll keep the old values for the previous configuration, right? I'm doing a very similar thing for the holes. So here I have M5, so I'm just editing the feature. These hole sizes are very common. I think we want to switch to an M8 for the question. It says M8 here, X1 for the bottom tapping hole. And again, slightly different option, but I still have this button here for configurations. I can decide whether or not I want to apply this feature to this configuration, all configurations, or specify specific ones. I can click on that and then I can turn them on and off. And again, in this instance, all I'm trying to do is only change the size of the hole for this new configuration. So I'll click on OK, click accept, and repeat that same process for the M5s on the base. So again, going to configurations, I can say this configuration, OK. Doesn't matter what order I do this in. Click accept. And now I've got, again, my holes are set to a larger size in this configuration. If I toggle back and forth, I can see it. Is that small holes, big holes? So pretty straightforward. You do want to be careful when you're doing this, especially on a CSWP, that when you change things, you're not breaking stuff. Applying changes to just the current configuration is the most conservative change. Applying it to all configurations is the most likely to cause issues because you're changing a bunch of things all at once, right? So when in doubt, I would suggest you only apply the change to either selected configurations, where you're doing that like only the specific ones, or to the current configuration, where you're less likely to break things. And I think there's one more thing it wanted us to do on there. It wanted us to set the 20 millimeter height dimension on the side hole guide sketch to 15 millimeters. So on here, the side hole guide, I would just double click that. That brings up the dimensions inside the view space. So I'm actually edit the sketch. And then I can double click on the dimension. And again, I have this drop down menu here. I can say this configuration, I want to be 15. just if you know that those things are there and you kind of have some idea where to look for them, it's pretty easy to find those and to make those changes. So any questions on the changes I'm making to just this configuration? So far, all of those were changes that only apply to my big configuration and are not going to apply to my small configuration. Yeah, so I double clicked on the symbol next to the name and it'll show me the dimensions associated with that feature. And that's true for pretty much everything, right? All right, the next thing it wants me to do is it wants me to skip the middle hole instance of the flanged hole pattern 1. And I did rename these to try and make it easier for you guys to find the thing I'm talking about. That's another thing they'll commonly do for CSWP, just to make it clear. Usually they're non-descriptive, so they'll say like feature A6, like edit feature A6 to do da 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 da. But be aware that you are going to have to find things based off of their name in the model tree. On here, I'm going to edit this, and you'll note that I have these drop downs now for all of these things, so I can change all of these things independently for this configuration or all configurations. What I'm doing to get this pattern is I actually have patterns in both directions, and I'm using the line to specify the length of the pattern. So in this case, it's just from this point to that point, evenly spaced with 5 entities, which I'm not asking you guys to change, but you can see how this automatically maintains spacing rather nicely. And then to skip the ones in the middle, down here, you can specify which instances of a pattern you want to include or exclude. So to exclude these middle ones, all I have to do is click on them and it brings them in. And they toggle, so I can click them and bring them back, in and out. So if you don't know that you have the ability to kind of skip things and do patterns, you might make that as 2 or 3 features as opposed to just a single feature, right? Maybe that would be 2 patterns and a mirror or something. But if you can skip and use these this modality to make things faster, it will help you. And again, I want that to apply to all configurations. So I think I'm good there. I didn't change any of these to just be a single configuration, I hope. I can double check it just by going and ticking on the small one. You can see that it's still missing there, which is great. And then the last part is adding the rib. There's lots of ways of doing this. Honestly, just a thin extrude would be fine. I'm going to use it using the rib tool just because it says to use a rib. So I'm going to draw a line on the front plane from the corner at the bottom of the base up to the top. I'm going to give it an angle of 45 degrees. I'm going to accept that. I'll go into my features rib tool. It tries to intuit the direction I want based off of what I've drawn. That looks okay. I do want to set the thickness, global variables, wall thickness, accept. And then I want to mirror that. So I'm going to mirror that about the right plane. Features mirror. Just going to make sure that looks right. And then I want to make sure that this is actually going to show up in all of my configurations because this is supposed to apply to all configurations. So I'm going to right click on this, go to configure feature. You'll notice here that in the default one, since it didn't exist when that configuration was made, it's actually suppressed. So if I don't want it to be suppressed, I can just uncheck that box, hit apply. Same thing for the rib here. I can right click it. I can go into configure feature, check and make sure that it's not suppressed. And if I want it to be suppressed, I could suppress it on each configuration. Click OK. And now I can toggle back and forth between these two things and just make sure I'm not breaking anything.
So when you change one, did it change the other one?
No, these two holes are independent. So I had to change one and then go and change the other. Well, so the default one just has the original hole size. When I changed the bigger ones, I made sure my changes are only applied to the current configuration. So in the configurations here, when I changed it, I just made sure the change was in this configuration, not in all configurations. And then the original one stays the way it is, right? And the way they do the CSWP is, it's not like you couldn't answer this question by making this as separate parts or something, but they just give you like 5 different questions, right? By doing one change and then making another 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 change, And if you're doing it the way they're asking you to, using the appropriate combination of configurations and stuff, all of those changes are super easy. And if you're trying to do it by, some other methods, it's going to be really hard. And so it's pretty much just a time game if using the correct pictures. On this one, I do need to evaluate, so you get the mass properties. I would really recommend you guys copy and paste from the evaluation command. So if I copy this, I'm just gonna use Control and C to copy, and I should be able to come into my quiz and paste that in. Be careful you don't have like extra spaces. And then I'll come back down here. It wants me to answer the same thing, but just for the other configuration. So I'll go back to default, wait for it to load. Hopefully I didn't crash all work right there. I toggle back and forth between big and default like 3 times. No, it doesn't want to work. You do want to close the mass properties tool between changing configurations because it won't actually update unless you close that window and open it again. It doesn't. It says I'm trying to edit something.
I just had a quick question about the rib.
Yeah, go ahead, Wyatt, or read.
For the instructions for it, it said to put the width at the flange width.
Yeah, so that was a typo.
Oh,
Yeah.
okay.
So I was trying to mention that halfway through the quiz, and Stefan noticed it.
Okay.
I'm not sure if you heard that or not.
No, I didn't. That's okay.
Yeah. I'm just going to save all, close this. I'll try opening it again. I broke something. I don't know what I did. I don't know if I accidentally deleted one of the solid bodies or something. I don't have a solid body in here for some reason. Yeah. I mean, Control Z I can't do anymore because I closed the part. Well, so I saved it, and then I made the changes. I can re-download it. There it goes. It doesn't have my flange anymore, though. Maybe mirror. They're not showing as being suppressed currently. I don't know why they're not showing up. That's weird. Feature flange hole pattern failed to rebuild. That's weird. It's weird that it made this error like after it was working fine. And it still has all these features in here that seem fine. It just seems to think that the solid body for the part is gone. I don't know why. I think I corrupted the file when I closed it. I'm just going to re-download it. It was like 91.96 or something. I only know that because I just made this morning. So, all right. Questions on that one? Pretty straightforward. Let's go ahead and download the original box flange. If you want to use your modified one, you can too. It doesn't really matter. I'm going to delete my messed up one. And what I'd like for us to discuss today is some of the different tools that we have in SOLIDWORKS simulation to allow us to better design and evaluate components. So in design for manufacturing, we talk about using the simulation tools to evaluate kind of stress fairly generally. We don't talk a lot about the direction of the stress and the types of loads that can be applied and how that affects the strength of the component. So that's kind of the topic of the week for us to present. And we'll talk about some more advanced features in here as well, depending on how much time we have. So to do this, I want you to start off by making sure you have the SOLIDWORKS simulation add-in turned on. Most of the things we're going to look at today are going to require that full simulation kit. just the express simulation does not have enough features for us to really look at the simulation results in detail. Make sure you've got that turned on. Go to the simulation tab. We're going to start off with a new study. And we are going to be doing this in a static kind of normal FEA environment. And we'll look at some of the design tools as well, although we probably won't have time to get into that until class on Wednesday. You can call it whatever you want. I'm just going to leave the static one as the default. And we've talked before, in previous classes about fixtures and loads. It's important that we define the fixtures and loads appropriately for our design. In this case, what I'm going to do is I'm actually going to use a couple of different types of loads with some pretty simple fixtures, just so we can visualize what happens to this part as we load it in different directions. So the first thing I want to do is basically an actually loaded member. So I'm going to go into fixture geometry, fix geometry. And I'm just going to fix the bottom of the part. And then I'm going to go into loads, force. I'm going to put a load on the top of the part. And I want to make this a pretty big load. So I'm going to use 10,000 newtons. Now keep in mind a newton is a pretty small unit of force. And carbon steel, which is the material for this part, is pretty strong. With just those two simple configurations, I'm going to run this study. What we should see with this is that we have a fairly even distribution of force throughout the part, with the exception of the actual flange. Since we haven't designed this to really hold force based on the flange pattern, we've just fixed the bottom. The force is going to almost ignore that bottom flange. We do have stress concentrations around the holes, but our maximum stress here is still well below our yield strength. So here we have 1.36, sorry, 1.363. This is in 10 to the 8th, so that'd be 136 megapascals. The mega being the times 10 to the 6, right? And our yield strength is 220 megapascals. So we're still well below the yield strength of the material on this. What is this telling me from a design standpoint? If I am designing this and I expect this to be the loading condition of the part, do I need the flange? Probably not. It's not really carrying any load. The load is down at 2.2 times 10 to the third. Most of the time, if you don't have a member that's in some kind of complex loading condition, you don't need a large base of support like this. Now, maybe if I was pulling it the opposite direction and using bolts to hold it on, that might justify the existence of that flange, right? So I want to look at a few ways of kind of decomposing the values in here before we move on to that step. But keep in mind, that's kind of where we're going to head to, is adding some more kind of complexity to how we're loading this part. So in the results, you've seen a lot of these before in terms of the chart options, the settings. Probably worthwhile for me to just review these. These first 3 sets are actually all part of the same menu. So if you click on any of those, you get the same options as tabs here at the top. This gives us the basic definition of the plot. The stress that it is showing by default is von Mises stress, which is a non-directional magnitude of stress kind of measure. So it's not telling me the direction of the stress or the type of stress. It's just telling me kind of, you think about the speed versus velocity. It doesn't care what direction that stress is being applied. What you can do is, if you care about the directionality of the stress in the part, is you can change this to show whichever direction you want based off the coordinate system of the part or a user-defined coordinate system. So in this case, what I want to do is I'm going to change this so we have stress in the X, Y, and Z, shear in the X, Y, X, Z, X, Z, principal stresses. There's the von Mises, which is the default. And then there's also different ways of kind of different error modelings for that non-directional stresses, which is all 3 of these. So go to the stress in the X direction, which you'll note is kind of along the short axis of this. And what we can do is we can just leave the rest of these as kind of default on the green check mark. What happened to our stress values? I mean, very broadly. Our stress before, takes a little bit of memory, remember, was 130-ish megapascals. What is our maximum stress now? 9.2 times 10 to the 6th. So it's 9 megapascals. So why did our stress using the von Mises go from having a magnitude of 130 to having a magnitude of 9 by changing it from being kind of that von Mises stress to just the X direction? May I guess? What is the direction of our load? That's normal to that top surface, right? But in terms of X, Y, and Z, if I try and line that up, you guys see the Y right there? So which axis is aligned with the force that we're applying? The Y axis, right? So if I'm loading in the Y axis, I would expect most of the normal force to be in the Y direction. So in this case, this part, right, has very little force in the X direction because I'm not applying an X force to this, right? So I wouldn't expect to see a very large force in the X. And if I were to swap this, I'm going to go back into my edit definition. I can change this to the stress in the Y direction. Looks a little funky. You can see we're still getting lower values, but closer to what we had before. And the stress concentrations are a little bit different than what we had before, but still considerably less. If we go to our Z direction, we still have lower. We go to our shears. Very low in the XY, which is this plane, right on top. And we can go through all of these one by one. Z direction shear. And still reasonably low. And we can go to our YZ shear. And there we've got some pretty significant values, 34 times 10 to the 7th, right? And we can kind of see that none of these components is of the same magnitude as the octahedral stress. And really, the total stress is going to be kind of like the root sum of squares of all of these components. So we're decomposing and figuring out what the directions of the stress are by looking at these different options. Honestly, I was expecting the stress in the Z direction to be a little bit more significant, but it looks like it's reasonably well distributed, probably because our stress concentrations are located around these holes, and that's warping the stress distribution around that circular spot. So again, we always go back into our von Mises. See that whole thing again. I didn't interpret that right. Yeah, 136 pascals. Does that kind of make sense to everybody? You care about the stress distribution and the direction of the stress mostly when you are changing the geometry of the part in some substantial way that is going to change how it responds to different loads. So this is probably not the best example because that actually loaded stress is very simple, but we can change this to have other different kind of stress distributions reasonably easily. So let's do that. I think the first thing we can look at is going to a moment being applied to this part. And what I'm going to do here to keep this simple is I'm going to get rid of this fixture. Just delete it. And this force. And what I want to try and do is add a bending moment to this part. I don't know if I want it on the front face or the back face. It probably doesn't matter. I'm gonna go in the model. I want to define an axis that I can use for my bending moment. I'm gonna use the intersection of the top plane and the front plane to create a reference axis right on the back of this part. So go into features, curves, reference axis. And then I'm going to use this, the intersection between those two planes. And then this axis one, I can use that to define basically the center of rotation of an applied moment. Do that one more time so you can all follow along with that. I'm just selecting the front plane and the top plane. Using control to select both those planes, getting reference feature axis. And I've got that on here. Now what I can do in my study is I can use that axis to apply a moment to this part. So I'm going to flop this a little bit. I'm going to fix the back side of the plate. Fix geometry. Yeah. And then I'm going to apply a moment to this large flat side. So in loads here, do torque and moment, same thing. The face I'm going to apply it to is this whole face, but the axis, the direction of it is going to be my axis too. And you can kind of see what this is doing is everything that's on the top side of the axis is going in, everything on the bottom side of the axis is coming out. And so that's going to torque that part. And I'm going to give it a value of, let's say 1,000 Newton meters. Newton is small, but a meter is big. So I think this is going to be closer to a failure condition. I'll run this study. So in this case, we've well and truly broken this part because our yield strength is so much, higher or lower than our maximum stress. And in a condition like this, we can see where those stresses are causing this part to fail. And honestly, adding some webbing to this, some ribs in the long direction could significantly increase the strength of this part. But if we want to look at a more detailed view of where the actual stresses are high, we can isolate regions of the part as well. So in addition to the direction of the stress, we can look at specific locations to further isolate these definitions. So what I'm going to do is I'm going to go into my chart options. Actually, it's in definitions. So I'm going to use true scale. Yeah. So that the deformations are not exaggerated. And then in here, I have all these different options that I can use to look at different regions of the plot. The first thing to look at here is the section clipping. So what that's going to do is going to allow me to cut a part in half, just like I would for a section view, inside my part view. A little bit kind of less interesting there, but if I come to my right plane, and then I offset until I'm in the, oh, too far. Let's just do 12, 10. Not remembering the size of my parts. We can offset to see kind of what the distribution of stresses are inside the actual part itself, which can be very helpful for us. And again, you can use this in combination with the previous tools. So that way you can look at the direction of the forces inside the part, as well as on kind of the general surface of the part where you can't see it. I guess I should be more specific as to why I did the definition here to do true scale. If you use the deformed scale or a largely deformed scale on this, it makes it difficult to find the locations inside the parts. because all of the reference planes are based off the undeformed shape. And so if you have a very large deformation inside the part, seeing where those stresses occur can be difficult. And if you want to, you can go into the definition on here and you can use an undeformed shape if you just say user to scale 0. And it won't show any deformation at all, which works fine. So that's the first thing we can do. We can clip that out to look at just side parts. The next thing we do is we can do this ISO clipping. And what this is going to do is going to hide any stresses that are above or below a certain value. So in this case, it's clipping out everything. That's clipping out nothing. The little black slider on the right is the cutoff point. So in this case, it's showing everything that has a stress that's less than this value. You can see it kind of bring it input out. I can flip that. I can show the things that have a stress greater than the value. This is really helpful for me because I can very clearly see that I have a very small mass of the part that has a failing load in this criteria. Well, maybe not a small mass of the part, but I have a failing load, or the stress concentrations are really isolated, right? You have these very high stress concentrations in a very small section of the part, which really just means that the fillets that I'm using inside those corners are not distributing the load sufficiently, right? And I need to add some material there to help ease the transition from the top to the bottom of the part. And probably I need to make the whole thing thicker. I can go to the thick configuration, rerun this, would probably be okay, right? You can also use this for both sides. So if you want to have one side crop low and one side crop high, you can kind of sandwich things around and get multiple crops. So you can look at just the regions that have a strength within a specific region or outside of specific bounds. You can do that as well. If you want to isolate that to the surface, you can also combine that with other surfaces to cut things out and do ISO cuttings. Any questions on the section clipping or the ISO clipping? The probe tools here allow you really just to look at specific points, which is helpful if you want to look at certain values. I don't tend to use that very much because most of the time I'm concerned about the maximum values and then the volumetric area over where that, so that the volume is the volume over which those stresses are applied. So I tend not to use those quite as much. And then you have similar options for displacement. So if you want to do the same thing, you show that. Let me hide that one and show the displacement plot. Again, this is similarly user deformed. If you don't want to see the full deformed shape, you can, but you can crop this out in the same way as you would. If you're looking for actual values on the displacement chart to figure out how much things are moving, sometimes it's easier to measure that rather than to visualize it. And you can have a 0 deformation scale on this and just use the magnitude of the displacement. And also, like we did in the stresses, we can look at the displacement specifically in different directions, which looks like most of this is in the Y. So we can see the Y displacement there. This whole beam here looks like it's being stressed a little bit, collapsing a little bit, moving a little bit. And it's also important to note that 0 on this is actually pretty close here, the green. And then the positive displacement is being showed in red and the negative displacement is being showed in blue. So really the center isn't moving. It tricked me. Let me turn off my ISO clipping. I'll reset. There you go. So this toggles on and off. And you can see that it's going down and up. Just gonna see that? The direction of the displacement is shown there. The other thing that's important to note there, if I use the resultant displacement, see how all the down and the up have the same magnitude, opposite direction. So if you want to know direction specifically, then that can be helpful looking at these in X, Y. And I don't think we have a significant amount of displacement in like the Z here. A little bit, not much. And these are all negative. So as it's bending in, moving in the negative Z direction. I'm not sure why both sides are looking at moving in the negative Z. I would expect one to move like left and the other move right. I don't know, very small values. Questions on that? All right, we're gonna spend some more time looking at different stress distributions and how we can use that to revise our designs in class on Wednesday. So I'll see you all there for that. If you have any questions on your projects, you want to talk about those, I'll stick around for a few minutes. If not, then I'll see you all on Wednesday.
All right, have a good rest of your day.
All right, Mallory, buried.
Bye.